Hello everyone, I'm still the instructor. Although I have my haircut, I'm still myself. So in the last lecture, we talked about linear regression model. The task is I have input x is in R to the D, and I can extend it by a trivial feature, and then I say my input is R to the D plus 1, and my target is a real number. And for linear regression model, it says my hypothesis class is all kinds of affine transformations of the original feature, which is the linear transformation of the extended feature. So the hypothesis class is h of x is w transpose x, okay, such that w is in R to the D plus 1. Okay, so this is the extended feature. And in the extended feature space, we have D plus 1 dimensions, and it's a linear transformation. Okay. Then the training set, so this is my task hypothesis. And the training set is, okay, I have a set of experience, which is x, m, with its true target, Tm, where m from 1 up to m. Okay. And my training objective or my training loss is, in the usual case, we use the mean square error. So this is my mean square error. Is 1 over 2m. So I average over all the samples. And I can say my prediction, h of x, m minus tm. Okay, and then I take it square, but I sum them together. Okay, so for each of the data sample, I have that much difference, and I make it a square, and then I take the average. And alternatively, we can represent it as a vector matrix multiplication, which is, suppose I have that much samples, and suppose my x is defined to be, this is my design matrix. I just stack all the samples together, 1 up to x2, so on and so forth, until xm, capital M, which is m by d plus 1 dimensional space. Okay, then my prediction, so my prediction would be y is, so this is just y, okay, so this is just y for the m data sample. So y would be xw, that's it, which is r to the m vector. Okay, and my loss can be represented as 1 over 2m, and this summation square is the L2 norm square of xw minus 1. Okay. So our next plan is we're going to introduce a class of functions, which is known as the convex function. So convex function just means it's curving up. And we're going to show that the convex functions has very nice properties. Okay, it has very good optimality. And we will show that mean square error loss is convex. And eventually, we will present the optimization algorithm, for mean square error. Okay. So now we're going to touch the very rigorous math. But before doing that, I'm just going to motivate why we did a convex function. So our intuition is convex function is something curving up. But then the question is, for example, is this function curving up? Okay. So in the last term, I asked the same question. Some students said, yes, it's convex, but some students said, no, intuitively, it's indeed curving up. But the question is, are you curving up everywhere? So is this place still curving up, right? So if you don't have a formal definition, then it's ambiguous. It's subject to your definition. So that's why we need a very rigorous definition for convexity. In the following, we're going to discuss some standard analysis stuff, but we include it in the machine learning course because some of our students may not be very familiar with that. And some of us may forget about the basic calculus or algebra. And when I was an undergrad or grad student, I also forgot a lot of math stuff. So it's always good to review math once again. And also the techniques I'm going to introduce are very important for analyzing machine learning models. So it's really good to know when we study machine learning. So definition, a convex set. Okay, so before talking about convex functions, we're going to first talk about convex set. A convex set in X, suppose my set is X, which is a subspace of a D-dimensional space. So we're talking about a vector space, and we typically assume the vector addition or scalar vector multiplication are already there, and then we define the convex set as. Okay, so this is the definition of convex set. So it's convex if and only if. So this is definition, if and only if for any x and y in my set, and for any lambda in 0 and 1. So lambda is a scalar, so x and y are vectors. Okay, so I would say lambda x plus 1 minus lambda y is still in my set. Okay, so this definition says for any 2 points in my set, if I take the average, weighted average, it gives me a segment, right? It gives me a segment. And every point on that segment is still in my set. So example. So this set, okay, suppose let's have a circle. Okay, very nice. So now you see for any 2 point, in this set, okay, I only need to verify lambda from 0 and 1 without x 0 and 1, because if you have 0 and 1, then there are already x and y, and I already know that it's in my set. So I only need to verify that this segment, every point on that segment is still in my set. So suppose my set is this solid plate. So this is solid, okay? It's not a curve. Then this set is indeed convex, because whenever you choose 2 points, its segment is still there. Okay. So another example, for example, this set, I call it x2, is not convex. Okay, because I can choose x here, I can choose y here, and then I can choose lambda. So if I want to show a set is not convex, then I need to give you 2 examples and the lambda showing that this condition does not hold. Okay, so now I can say maybe x is here and y is here, and then I choose lambda such that lambda x plus 1 minus lambda y is here. Then if your shape, your set is this one, then this point, the middle point, is definitely not within your set, so it's not convex. And another example, my x is these 2 plates. Okay, they are solid, but they're disconnected. So any set that is disconnected, it's not a convex set, right? Because if something is disconnected, then if you can have a x, choose one x from one component, and if you choose y from other component, then if you connect these 2 points, there must be some point on this segment, not in your set. If all the points on this segment is in your set, then this is still a connected set. Right? So this is convex, still convex, and still convex. Oh, sorry, not convex and not convex. Okay. And maybe I can have a set like this. Okay, I include all the universe except this circle. Okay, so now next we're going to define convex functions. Okay, from X to R, where X is a subset of my vector space. Okay, so my input, so we restrict ourselves that the input of this function has to be some subset of the d-dimensional vector space. So it's still a vector space. If you put a mouse into my function, it's an error. It's a type error. So it's still a vector space, okay, as input. Then it's not necessarily the entire vector space. Maybe at some point, the function can refuse to tell the result. It's also fine. Then it maps to a real number. Okay, so we're talking about real functions. The output of this function is a real number. So f from x to d is convex. Is a convex function. Is a convex function. If and only if. First, I would say the domain of x. Sorry, the domain of the function. The domain of function, which is x. Okay, is a convex set. And second, the function is curving up, okay? But how can I measure if a function is curving up or not, okay? So now I can take any points, any points in the domain. So this is my X space. So this is my RD space. I told you how to visualize the high dimensional space. So I just plot a line and I say this is RD, okay? If you feel it's not satisfactory, then you show it's a curve, okay? Something like this, okay? But we just put a line. And I choose any 2 points in this space, okay, in the domain of X. Okay, then if it's curving up, then it means that in the middle, the function value should be lower than the average of your function values. So, okay, so this shows the average of these 2 function values should be lower than the function value of the average, right? So I would say, what is average? The average is the weighted average by lambda, okay? For any x and y in domain of f, which is fx, okay? So I call the domain of f is x. For any lambda still in 0 and 1, okay, in the middle. Then the function of the average, so the function of the average input, okay? So this is my x and y, they are the input. The average of the input is this point, okay? So this point is lambda x plus 1 minus lambda y. Okay. So the average of the input and you feed it into the function and gives you the value should be less than or equal to, okay, the average. So I would first compute the function values. And then I take the average. Okay. So if you first compute the average of an input and you compute the function value, that should be less than I first compute the function values and then I take the average. So if you satisfy these 2 conditions, then it's a convex function. Example. Okay. So I would say f of x is x. Okay. Or maybe x plus b, or maybe kx plus b. Okay. So k and b are real numbers. So obviously it's an affine function. So the function of the average of input is precisely the same as the average of function values, okay? So in this case, this is equal. So equal is also a special case of less than or equal to, so it's convex, okay? So now it's a little bit surprising if you have only some vague intuition. You know, I'm saying this function is curving up, but it has zero curvature. It's a line. It's still convex. Okay, it's not strictly convex, but it's still convex. Maybe f of x is x squared. Okay. Then you can verify it. You know, it's x squared. Then you know you can verify it. Any points here, in the middle, the line is higher than the function. Okay, so it's also convex. But with this very rigorous definition, now we can analyze if this function is convex. It still looks curving up in general. Okay, it's still curving up. But is that function, is that convex? So the answer is no, because now I can choose 2 points. So to show that a function is not convex, I can choose 2 points. I have the right to choose 2 points, and I also have the right to choose lambda such that this condition does not hold. Okay. Now I have to choose these 2 points, and I can choose maybe lambda as middle. Okay, we just have one lambda in the middle. That suffices. Okay, I just have one lambda in the middle here. Then the function of average input is higher than, okay, it's greater than the average of the functions. So this is not convex. I can show more examples. For example, this function doesn't look good because it has a point here that is not differentiable, but it's still convex. Okay. But what if a function is something like this? Okay, this point is not valid, it's not defined. Then the domain of this function is maybe minus infinity to 0, and then 0 to plus infinity. Okay, so this function is not convex because the domain itself is not a convex set, right? The domain is not a convex set. Because you know, I can choose x is -1 and y is 1 and lambda as half, then you know, then lambda x plus 1 minus lambda y is 0 is not in my domain of f. Okay, so the domain of f is not a convex set. So we are clear about the definition of convex sets and convex functions. But the problem is, if you want to show a function is convex, if you follow the definition, it's too complicated because you have to show the condition holds for any 2 points in your domain and for any lambda here, okay? So it's not an easy approach. So now we're going to show a few equivalent conditions to a convex function. And next time, if you want to prove a function is convex, you can use the equivalent conditions, and that will be much simpler than working with the original definition. Theorem. Suppose f is a twice differentiable function. Okay, so this means f is smooth and the derivative of f is also smooth. Okay, the derivative of f is also smooth. Then the following conditions are equivalent. A, f is convex, so this is my goal. B, which is known as the first order condition. First order condition says for any x and y in my domain of f, so x and y are vectors, f of y is greater than or equal to f of x. So they are all scalars because the function f is a real function. Plus the gradient of f of x at this point, okay, at this point, at which point? At this point, okay, at x point. Transpose y minus x. Okay, so they are vectors. So I can represent vectors with a bar. So these are vectors. All other things are scalars. And of course, the gradient is also a vector. So this shows, so just a reminder, what is the gradient? The derivative or the partial derivative of f evaluated at x with respect to x, okay? It's defined to be, so suppose x is x1 up to xd, okay? Suppose x is a d-dimensional vector, then the gradient or the partial derivative is you treat every dimension as a variable and all other dimensions are fixed constants. Then you compute the partial derivative. It gives you the partial derivative of x1 f x, okay? x2 f of x, so and so forth up to xd f of x. Okay. Okay, so the gradient is still a d-dimensional vector. So pictorially, this condition says I have a function and it's curving up. The gradient is the slope of the line that is tangent to the shape, okay, at some point. So let's say this is my x and this is my y. Then the gradient at this point is the slope of this line, okay, of this tangent line. So this is my gradient. So in a one-dimensional space, the first order condition says my y for any y. So y can be here, can be anything. So for any y can be anywhere here, okay? So my y, the function value at y should be greater than or equal to the function value plus the gradient or the derivative times this line. So I can zoom in a little bit. And this is my df of x with respect to dx. So I would say this is a one-dimensional case, okay? Then this term is just the gradient times y minus x. Suppose y is here, okay? Suppose y is here and x is still here. So x is still here. Then y minus x is how long is this? And this is the slope. Okay. So the slope is the ratio of this segment divided by this segment. And you multiply by this length, then you get this part, okay? So this part is precisely df of x by dx times y minus x, okay? But the convex function says it should be larger than that. So this point should be larger than this point, okay? So the line tangent to a function is always the lower bound of the function. The function should occur in the upper half space of your tangent line. Okay, so this is one-dimensional case. But how about a multi-dimensional case? Then this is a vector. So this actually says how y changes. So maybe this is my x1, this is x2, okay? And this is y, this is x. So they are vectors. Then this is my function. And this is my tangent hyperplane, okay? Now I'm getting a salad bowl and also it's green, it's nice, okay? So now this is my space and this is the tangent line, but this time it's a tangent hyperplane or tangent plane, okay, at this point. And how much f of y changes with f of x is how much you would change in the first dimension plus how much you will change in the second dimension. So that's why it's the inner product, right? So this is the multi-dimensional case. So I would say this is, suppose I have two dimensions, then this is f of x, okay, plus how much you would change with respect to x1 in the first dimension of x. y1 minus x1. So how much y changes x in the first dimension plus how much you will change in the second dimension, y2 minus x2. Okay, so this is the intuition of the first order condition. So basically it says a linear hyperplane is the lower bound of the convex function. See, second order condition. So for any x in my domain of f, the second order derivative of my f of x, okay, is positive semi-definite. It means the eigenvalues are all positive or zero, it's not negative. Let's remind ourselves about calculus again. So the second order derivative is you first compute the first order derivative and you compute the partial derivative again. But the first order derivative gives you a vector and you want to take the derivative with respect to a vector again, then you get a matrix. Okay. So it's by definition, okay. So you first do partial derivative with respect to x1 and you do it with x1 again, f of x. And then you do it with x1, but second time you do it with x2, f of x, so on and so forth. But here you do it with x2, and then you do it with x1, so on and so forth, okay? It turns out there's a matrix, so the order how you take the derivative doesn't matter much, okay? And x2, partial x2, so on and so forth. So the second order derivative is known as the Hessian matrix or Hessian matrix. And suppose X is d-dimensional vector, then the Hessian is the d by d matrix. Okay, is that clear? And what does the second order condition say? The second order condition says this matrix is positive semi-definite. It means all the eigenvalues are greater than 0. Suppose X is 1D. So in the 1D case, X is a line, and I can plot it here. So this is X and Y. Then the second order derivative of a point is the curvature at that point, okay? So if the second order derivative, which becomes f prime prime x, or you can call it t squared by the x squared f of x, okay? And if it's positive, then it's curving up. If it's 0, then it has no curvature. It's a flat line at the local point. And then it's less than 0, then it's curving down. Okay. If you don't believe that, you can try y equals x squared, then the first order derivative y prime is x, 2x. And the second order derivative is 2, so it's positive, but we know x squared is something like this, so it's curving up. Okay, for every point, it's curving up. But how about the high dimensional case? In the high dimensional case, so we not only consider the curving up in one degree of freedom, but I have other degree of freedoms. Maybe I'm curving up in this direction, but curving down in that direction is possible, right? So one example is I'm curving up in this dimension. So it's really hard to draw. Okay, maybe it's curving up in this dimension. But I'm curving down in that degree of freedom. Is that possible? Okay, it's very hard to draw, right? You see, it's very hard to draw, but is that possible? Right? But it's definitely possible, right? You just put a curve like this, and then you put different curves. Then it's curving down in this way and curving up in that way. So this is known as the saddle point. Okay, and in saddle point, then then the eigenvalue associated with this degree of freedom is positive, but associated with that degree of freedom is negative. And this is not convex, not convex. Okay, it's not convex. And now I have get two saddle points here. So this is the real saddle, the whole saddle. You see, it's curving up in this dimension, right? But it's curving down in this degree of freedom. So you see your cross your legs over the saddle. So it's curving down in this direction. It's curving up in this dimension. So when the horse runs, you are still stable. Right? And this is another plot that I found. And this is another plot I found on the internet. And this is a computer plotted shape. And you see this is a saddle point. This is the saddle point. And you are curving up in this degree of freedom. So you are curving down in that degree of freedom, right? So in this case, some of the eigenvalues are greater than 0. Some of the eigenvalues are less than 0. And this is not convex. Because I choose these 2 points, okay? And I take a segment with that, and you see the function value, and I take the middle point. So now you see the function of the average input is greater than the average of functions. So it's not convex. And precisely, the second order condition here says, oh, this should not happen. It should be all degree of freedom should curve up, and then it's positive semi-definite. Proof. So I guess I can clear something here. Okay, proof. I'm gonna prove B2A and C2B in one-dimensional case, okay, in the 1D case. And for the remaining proof, you can complete it yourself, or you can read some references. So B2A says, I would like to show F is convex, okay? So the only tool we have at this moment is the definition. So we have to use the definition. And the definition says you have to verify any 2 points and any lambda, and you show it satisfies the inequality. So I start from for any x, y in my domain of F. And for any lambda in 0 and 1. Okay. Just for convenience, I just define Z as lambda x plus 1 minus lambda y. It's just for convenience. My goal is to show f of z is greater than or equal to, f of the function should be less than or equal to. Okay, so this is my goal. I cannot write it here. If I write it here, then this is not proof. This is cheating. This is my goal. Okay. So what do we have? I have this condition. So now I say for any x, y, z, I have this condition. So I can say f of x is greater than f of z. I just plug in y as x and I plug in x as z, okay? Plus, so this is z x minus z, okay? So this works, I call it 1. And I do similar things. I plug in y as y, and I plug in x as z, okay? So the z is still there. Okay. So this is my first order condition. And my goal here is, I know the first order condition holds, and I want to show it satisfies the definition of a convex function. So now I can say 1 times lambda plus 2 times 1 minus lambda. Okay, if you do this, then you get lambda x plus 1 minus lambda is greater than or equal to something, then you almost get it, right? So I say lambda f of x plus 1 minus lambda f of y is greater than, so the first term is multiplied by lambda, so lambda f of c plus. The second term is multiplied by 1 minus lambda, so 1 minus lambda f of c plus, okay? And the derivative of fc is shared, so I can pull this term out, okay? And don't forget that my first term is multiplied by lambda and my second term is multiplied by 1 minus lambda. So it should be lambda times x minus z plus 1 minus lambda y minus z. Is that right? Okay, you almost get it. This term is the same as here. And here, you believe after some arrangement, you'll get it. So this gives me f of c. So this term gives me f of c, right? Plus. Okay. So it's just a little bit calculation. So I can cancel out this term and this term. Okay. But I still have z, but I know z is a function of x. So I would expand it a little bit. So I put everything without z here. Then I have to minus z. And I know z is this term. I subtract z, which is this term. Sorry. Which is this term, which is I subtract z, which is minus lambda x minus y plus lambda y. So now this time it gives me these two terms cancels out. These two terms cancels out. Okay, this term also cancels out. So this term becomes 0. And of course, something times the 0, this is a 0 vector. And something multiplied by a 0 vector, you still get a 0 number, okay? So this term is 0 number. So this term is a 0 vector, and this term is a 0 number, and it gives me f of c. So now you compare with your goal, you get it, right? So this term is greater than this term. Okay, you get it. So this proves that if the first order condition holds, then the function must be convex because I showed the convexity by definition. C to B. Here, I only consider one-dimensional case. Okay, just for simplicity. But for high-dimensional case, I will briefly describe what happens with that. So I know the second order derivative is greater than or equal to 0. So I know the second order derivative. So f double prime of x is greater than or equal to 0. So this is my condition. Then I would show f is convex. Maybe I use the definition, or maybe I use the first order condition. Okay. So maybe I would like to do Taylor expansion. So Taylor expansion says, for any x and y, f of y is f of x. Almost, I mean. If you believe the function is a constant, then it's correct. But it's not a constant, then f prime of x times y minus x, okay? So you approximate a function by a line or by a linear hyperplane. But in here, it's just a line. Plus y minus square plus, okay? So now you have different versions of Taylor expansion. If you have an analytic function, then the series If you sum all these infinite terms, you will get exactly f of y. That is the definition of being an analytic function. But the original Taylor theorem says it's not f of x, but f of c for some c in y, x to y, okay? But without loss of generality, we assume y is greater than or equal to x, okay? Otherwise, you just say c is in y, x. So this is the original version of the Taylor theorem. So here you expand it to the first order. Then you have a residual term. And for this term, the derivative is not x nor y, but the derivative is some point in the middle, okay? So it's an extension of mean value theorem. So the mean value theorem says f of x and f of y. So the mean value theorem says if you have a nice function, the smooth function here, then f of y is f of x, okay? Plus some derivative here, some c, okay, times y minus x. It's the mean value theorem. So it says exists a point here, I have a point here, then the slope of this point is exactly how f changes as your input changes, right? So this slope is the same as that slope. But this point, I call it z, may not be x, may not be y. It can be some point in x or y. And this is the same here. So if you have a finite term for Taylor expansion, then you have the residual term, and this term, the derivative or the nth order derivative is not the end point. It may be some point in the middle, okay? So now I would say this is positive. I know it, it's not negative, okay, it's positive. And y minus x squared is also positive, okay, I know it. So that's why f of y is greater than f of x plus f prime of x, y minus x, okay? So now first order condition holds. So I know first order condition holds, then the function must be convex, okay? So this is the second order condition to first order condition in the one-dimensional case. So for the high dimensional case, I'm just going to show the roadmap, but I'm not gonna prove it. So for a high dimensional case, the idea is you segment this shape by a line. You segment the input, okay? So I can say, okay? You slice the input by any line, okay? And you see the function on that line, okay? So on that line, so this function, okay, on that line. So this is my function. If you show that the function cut by a line is convex for any lines, then the whole function is convex. It's jointly convex in the vector space, okay? So suppose this is x1 and x2. So if you show your function is convex in x1 and your function is convex in x2, it may not be jointly convex. If you can show that for any line, the function cut by this line or this plane, I mean, you use a line to cut your input space, then you show the output space, then you get a plane, two-dimensional plane. If the intersection on that plane is convex, okay? And if that works for any such plane, then the whole function is convex. With these extensions, you can prove that the second order condition implies the first order condition in high dimensional case as well. Okay. So now we just proved B implies A and C implies B, but there are some other directions and you can work with yourself, okay? And sometimes this can be relaxed. So twice differentiable function can be relaxed. And for example, when f is convex, then it implies the first order condition, and you only need to have the derivative exist on the x point. And you don't have to say the function is differentiable at all points. For example, I can say this function, okay? Unfortunately, it's not differentiable. It's not a differentiable function because there exists a point that is not differentiable, which is here. But still, my first order condition holds for all the points where it's differentiable, right? You know, if you have a point here, then the first order condition still holds. And if you have a point here, the line tangent to the function is still the lower bound. Okay. So for other directions, you can work by yourself. The last thing for this video is optimality. So I'm going to show what is the optimum value or the optimal solution for a function and how many kinds of outcomes. So we know if a function, non-necessarily convex in general is like this. So maybe, this point is optimal, but this point is also optimal locally. So we see there are different optimality. One is global optimum. Okay, it's the best for any point in the domain. And the other is local optimum. It's only best in its neighbor, but maybe it's also the best outside its neighbor. So definition, okay, so let f is a function from Rd to R, So from its domain, let's say x to R, it's a real function and its domain, it's a subset of Rd, okay? A global optimum So when we talk about optimum, we talk about the solution. So x, okay, x star in x, okay, is defined as for any y in my domain of f, okay, which is x. My f of y is greater than or equal to f of x star. Okay, so this point, this is x space, this point is x star. Okay, so global optimum says this input makes my function value minimal, regardless of what input you take elsewhere. Okay, and usually when we talk about optimization, we minimize something, so we hope my optimum has the smallest value. And also when in mathematics, when we talk about the best or the highest or whatever, it's usually not necessarily strict, so it's greater than or equal to. Okay, so if I have a flat region, as long as it's indeed the lowest point, here is still the global optimum. Okay, it's not necessarily strict. So this is global optimum. So for any y in my domain, local optimum. Okay, I say x in x is a local optimum if exists. So it's only local, okay, but I didn't mention how large is its neighbor. So I just say exists a neighbor, okay, exists a neighbor. So I call it epsilon greater than 0. I exist a neighbor. Then for any other point within this neighbor, okay, so I would say for any other point in the domain, if y minus x is less than epsilon, then f of y is greater than or equal to f of x star, okay? So let's say this is a local optimum. If I have a neighbor, so I don't require you that f of x star is the best in all its domain, but it's only around its neighbor. Then for any other points, as long as it's in the neighbor, then the function value should be larger than that optimum, right? So this can also be represented concisely as for any y in the neighbor of x with absolute distance, with absolute radius. Okay. So theorem. If f is convex, still from a domain to a real function, and x star is a local optimum, then f is a global optimum. Okay. So this is a very nice property of convex functions. So it only says, I have a function. I don't know how the function is outside my neighbor, okay? As long as I know the function, a point is optimum its neighbor, okay? It's the best point in its neighbor. then I know it's the best point globally, okay? For any other points, it will not be better than that. So this is a very nice function of convex functions. It's not necessarily differentiable. For example, my f of x is okay, still x squared, but my domain of f is 1, 2, 2. I have 1, 2, 2. Okay. You know, there's no point which has a derivative of 0, but still, you know, 1 is the best point in its neighbor. So I can find a neighbor here, okay? I can find a neighbor here. It's the best point. The point 1 is the best point in this neighbor, which is here. But still, I can find the neighbor, which is maybe 1 to 1.2, okay, in this neighbor. Then for any point in this neighbor, the function value is larger than that of this point. So the 1 is still the global optimum. You don't have to verify these things. So this is the very nice property of convex functions. Proof. How can I prove that? So first, I cannot use any derivative-based proof because I didn't say f is a differentiable function. So I will try the definition of global optimum. So I want to show its global optimum, then I have to show for any y. So you have the right to give me an y. Then I have to defend myself that this y is indeed has a greater function value than my optimum. Okay. So for any y in my domain of f. Okay. Then my goal is f of y is greater than f of x. Star. Okay. So the tool we have is f is a convex function. We know for convex functions, we have some inequality and connects the function values of different points, and it's greater than or equal to something. So probably we want to use that property, just the definition of convex functions. So suppose this is my x, this is my optimum. And this is my y for any y. It can be any y, it can be here, it can also be here for any y. Okay, and I know x is the best within its region. Okay, exists some epsilon, x is best for any point here. Epsilon is greater than equal to 0. Okay, so now by convexity, I can say by convexity, I know for any lambda in 0 and 1, lambda of x plus lambda of f of x plus 1 minus lambda of f of y should be either greater than or equal to or less than or equal to f of lambda x plus 1 minus lambda y. Okay, and I just figure out. So the average of the function value should be greater than or equal to the function value of the average input. Okay, how about I choose, so I can call it z, this term as z. How about I choose z within my epsilon? So I would like this to be my z. Okay. So if y is within my epsilon neighbor of x, then it's proved. So if y is already here, then this condition definitely holds. So for a non-trivial case, I could say y is not within my epsilon neighbor. Okay. So I guess I don't need the settle here. Great. And I have more space. So I can safely assume y is not within my epsilon neighbor. If it's within my epsilon neighbor, it's the better case. I can just show it. I can just show the function f of y is greater than f of x star. With this x star. Okay. How about I choose lambda such that, okay, so the difference between y minus x is the length of y minus x star, okay? So this is how long is this distance, okay? And I would pick the z within the epsilon neighbor. So I would say X would weigh by I would say this is y minus x star. So this is still this distance, but I would extract it by epsilon divided by 2. Okay, does it work? So totally I have that much, and I would weigh x a lot. So it's almost y minus x star, except that, okay, I extract that by 2. Then I can show that lambda x star plus y minus lambda y, so this is what I define as z, okay? I can show c minus x, the distance between c and x is epsilon divided by 2. X star. Okay. Okay, I can cancel these terms, and I have the absolute value of minus epsilon divided by 2, of course, right? I just designed the lambda like this, right? I'm very slow in math, but you can just show it by do some trivial calculations. So I'm safe, okay? I can say for this time, this z is within my range of epsilon neighbor of x, okay? Then what do I have? So I would have lambda of x star plus 1 minus lambda fy is greater than f of z. Right? So f of y is greater than f of z. Lambda of f of x star, so minus lambda f of x star divided by 1 minus lambda, because 1 minus lambda is also in 0 and 1, so you can just divide it without changing the inequality sign. And I know f of z is greater than f of x, so this is greater than or equal to f of x, which is actually x star divided by 1 minus lambda. Okay, so this is, I know f of z is greater than f of x star by the local optimality. Then I have x star 1 minus lambda divided by 1 minus lambda. It's f of x star. So this shows that f of y is greater than or equal to f of x star. This shows x star is the global optimum. I start from a local optimum and I use the property of the convex function and I show it's a global optimum. Okay, it's a very good digression to convex functions. For the next lecture, we're going back to the linear regression model and we show mean square error is a convex function and how can we solve this problem. Okay, see you next time.